What about Lychrel numbers? Symmetry is synonymous to harmonious proportion and balance. In mathematics, symmetry refers to an invariant under some transformations, mainly translation, reflection, rotation, and scaling. With palindromes, the reflection property is the topic of the discussion. A palindrome is a sequence of digits which reads the same backward as forward. The image in a mirror is the same as the one in front of it. For example, 101 and 131 are the first palindromic prime numbers with 3 digits, while there are none with 4 digits or any greater even digits numbers. To find the infinity of integers of the pyramid shown on the board is certainly a Herculean task, but happily it is not the subject here. The famous palindrome Nipsun Anamamatami Monan Opsan, wash your sins, not only your face, is a Greek palindrome which was inscribed upon a holy water font outside the church of Hagia Sophia in Constantinople. The word palindrome was introduced by Henry Peacham, in 1638, according to Wikipedia. It is derived from the Greek roots, polis, again, and dropos, way, direction. A different word is used in Greek, karsivakos, karsenic, literally crab-like, to refer to letter-by-letter reversible writing. The Wade-Van Landingham's algorithm consists in adding a positive number to its symmetric counterpart. A Lychrel number is a number that cannot form a palindrome through this iterative process. This process is sometimes called the 196 algorithm, after the most famous number associated with the process, most famous just because it is simply the smallest such known integer. Such known effectively but not yet proven as such. The purpose in this video is to show that the palindromic occurrence, when it occurs, is not an invaluable achievement, but a mere youth event, a banal incident. We will set up a measure of the gap to palindromic event and its evolution during the process in order to justify this cavalier assertion and at the same time show how similar all integers are when subjected to this Wade-Van Landingham's algorithm. However, what initially seems to be an evidence in base 10, will take later on, a different turn in base 4 or 2, risking to dispute the actual nature of integers in any base and leaving more questions than answers, as summarized in the title of the mathematical article given in reference at the end of the video. This may seem a provocative banter, but its meaning is quite elastic, expands or contracts, as this video progresses. Years of continuous calculations have been carried out on certain numbers, including the presumed first one of them, in order to confirm the absence of a palindrome. The research work thus seems to be mainly focused on the brute force method of launching a program in the hope of setting a record, knowing that the only real record is in fact infinity. We propose to assess the gap with palindromy and gauge within a few tens of seconds the interest of conducting such an investigation. We will show that a massive and prolonged search is doomed to fail regardless of the initial number in the range of number sizes of current records, so for 196 also. So let us begin with the integer 196 and look how the algorithm evolves. We give to the initial number a zero-step assignment. At each step, we add to the current number its symmetrical. At step 1, we find therefore 196 plus 691, which is equal to 887 in the second column of the hereby table. This second column is called usually the thread. What we do then is to get the nearest palindrome to the current thread value. We call it the associated palindrome and they are in the fourth column. When the adequate palindrome is chosen, the difference between the value of the current integer in the thread and its associated palindrome contains only 0 or 1 figures as shown in the fifth column. To evaluate the gap to the palindrome, we then very simply count the number of ones. This gives us a measure in the sixth column at each step of the error to a palindromic event. A graphic is then the best way to visualize what happens. We get an average linear evolution. Looking at such a straight evolution, the purpose to spend years of computers run off seems more a whim of a diva, or a mathematical fantasia, rather than a reasonable search. The interesting part is then to compare this evolution with a choice of other numbers. Let us make a trivial choice. So, we start with integers 0, 02, 03 up to 010. The viewer will distinguish those with the alternative choice, 1 to 10, very different, which would give numerous redundancies for the thread path, since 8, 4 and 2 are twins in regard to 1, as is 6 in regard to 3 and 10 in regard to 5 in this specific algorithm framework. Let us note that the graphic shows again an average linear evolution, but not only, as this evolution has also same slope and this slope is equal to the previous slope observed with initial integer 196. From there, one will not be especially surprised to find that any number in base 10 seems to evolve in the same way. The following numbers are delayed palindromes, meaning a palindrome is found after an unusual great number of steps. The qualificative great may seem presumptuous, but effectively it is not an obvious thing to find this records. Let us observe the tiny difference between Lychrel's numbers which never get a single point on the x-axis, and the non-Lychrel's numbers which do. The palindromic events occur really near the origin, the deviation from the average line being hardly exceptional compared to later spacings. So what? Is that all that is to say? In fact, no. We worked so far in base 10 with a deviation constraint on the same slope. But the main fact has not been raised so far, the deviation follows a random path. This is no more so when we investigate another base. In base 4 and 2, we encounter random paths as was the case until now, but also totally predictable paths. Choosing a number, if the path, immediately or after some steps, embraces the said predictable future, we call the number a Cheryl's number. That is where things get really interesting. Indeed, if there are both random and non-random paths in bases like 2 and 4, why not in some other base? Why not after all even in base 10? And if some number in base 10 is of Cheryl's type, isn't there some steps where any integer takes a totally predictable path? A lot more questions may then occur, like: what is the density of Cheryl's integers in the set of natural numbers in base 2? Are all integers Cheryl's integers in base 2? What is the density of Cheryl's integers in the set of natural numbers in base 4? Are all integers Cheryl's integers in base 4? What is the density of Cheryl's integers in the set of natural numbers in base 10? Are all integers Cheryl's integers in base 10? What is the density of Cheryl's integers in the set of natural numbers in base x? We didn't find anything in the mathematical literature on the Cheryl's subject, and the questions are open. Besides, the theoretical studies on Lychrel's numbers are apparently also very poor, except for Jason Doucet website. Therefore, the viewer is invited to have a further look on this subject at either of the following links. We wish you a pleasant reading. What about some comments underneath after that?